Thank you. First of all, let me start by thanking the organizers for giving me an opportunity to present this work. So today I'm going to speak about control of spatiotemporal chaos by stochastic resetting, and this is the work done with Camille Aron at Equal Normal and EPFL. So let me just start with the central message of the talk. I'll try to explain these things in red in more detail, but we discuss how spatiotemporal chaos in dynamical systems can be mitigated by stochastic resetting, by stochastically resetting them to their initial conditions. And we use the platform of discrete nonlinear maps and try to understand how Lyapunov exponent and butterfly velocity, which basically quantifies sensitivity to initial perturbations and ballistic spread, can be reduced by stochastic resetting. And we identify some critical resetting rate that induces a dynamical phase transition, meaning that your Lyapunov exponents and butterfly velocity basically vanish, effectively arresting the spread of information. And most of our results are analytical, and we illustrate with numerical simulations on logistic maps. So I'll try to explain the meaning of all these things. So let me start by stochastic resetting. So I guess a large part of the audience doesn't need to know what this is, already knows it. So the core idea is you basically return a state of a dynamical system to its initial condition at random times. So for some time it's doing its thing, which could be deterministic or stochastic, but at random times you reset it back to its initial condition. So that is the basic idea of stochastic resetting. So you have this particle, it is doing something, and at random times you reset it back to its initial condition. So with stochastic resetting, there's a nice renewal structure which is quite useful. So for example, the distribution of particles with resetting can be thought of as coming from two processes. One is up to time t, there is no resetting at all. So the thing is just doing its own inherent dynamics. And then you add all trajectories where the last resetting event occurred at time t minus tau, and then you integrate. So basically you are able to connect the usual dynamics with no resetting to the resetted dynamics. So this is the idea of renewal structure. So you have particles, any system which is dynamically evolving, and at random times you just reset it back to its initial condition and again evolve. Okay? So no matter what this dynamics is, typically what happens is if you go take t equal to infinity limit, this thing goes away and this is just a Laplace transform. So you basically resetting induces a non-equilibrium steady state. Okay, so that is the idea of resetting. So this is a very versatile tool. It's amenable to analytical calculations. It has been demonstrated experimentally. It is relevant for search problems. Relatively less is known on extended interacting systems, and it can also serve as a tool for dynamically generating correlations. Because you reset everything back to their initial conditions simultaneously, they can induce correlations like what Sanjib was talking about yesterday. So in this talk, the question we ask is, what is the fate of chaotic properties when they are subject to stochastic resetting? So imagine you have some system which is chaotic, which has Lyapunov exponents and so on, but if you stochastically reset it, how does it change the properties of chaos? So that is the question, broadly the question we are asking. And we'll start with some simple example of, we'll start with a zero-dimensional map. So this is a discrete map. So at time n plus 1, it evolves like this with some probability 1 minus r, and it gets reset with probability r. So here r is probability, just is bounded between 0 and 1. Later you can sort of extend it to spatial maps. Okay, so but the idea is you basically try to subject these things to resetting. Okay, so now, so how do you kind of tame chaos in these kind of maps? So this is, recall that this is my dynamical map. So one simple example would just be this: x n plus 1 is equal to 4. This is something everyone might have seen. This is an example of logistic map at maximal chaos. So, once you have such a map, you can always ask what the steady state is. You can calculate Lyapunov exponents. So you start with two infinitely close initial conditions and calculate the Lyapunov exponent. And now we ask the question: what happens if we reset this map stochastically at some Poissonian times? And you can ask what are the steady states and so on, and what is the renormalized Lyapunov exponent. Question is, does the Lyapunov exponent reduce or does it become zero, and so on and so forth. So you're kind of effectively trying to ask whether chaos can be engineered. Now, I mean, it's quite obvious that when you reset it back to its initial conditions, you're sort of presumably going to reduce chaos, right? So, okay, so this is, so it turns out that we can actually use some sort of a renewal formula that I sort of explained in my second slide, and these are our results. So you can get nice analytical expressions for the original Lyapunov exponent and the new renormalized Lyapunov exponent. So, and this R is the resetting rate. And then you can see that there's a critical resetting rate below which the Lyapunov is zero. And in terms for maps, what happens is you can actually write explicit expression for renormalized Lyapunov exponents. So the idea is basically you have any system which has some Lyapunov exponent, and you can try to connect the renormalized Lyapunov exponent due to resetting with the original Lyapunov exponent. And this is an example that I showed here on the board. You see that when there's no resetting, you have this Lyapunov exponent, and then this is how it behaves, and this is agreement between theory and analytics. And there's a critical resetting rate when the system becomes completely non-chaotic. So I hope this part is clear. So now we ask this question. So this is a zero-dimensional system. So now we ask this question, what about extended systems? So in extended systems, you can do the following. You have an extended system. You prepare 2 copies of the system with exactly same initial conditions, except in the middle. And then you ask, what is the difference in the trajectories between copy A and copy B, both in space and time? And typically what happens in chaotic classical systems is you get a nice light cone. Yeah. So it doesn't, in this formalism, it doesn't go negative. So basically, I mean, if you have a damped harmonic oscillator, for example, there the Lyapunov is negative, but here at most we can hit 0 Lyapunov. Yeah, it's not, this is what analytics gives us, but I think it's not, it doesn't go negative. That's an important point I should have said, yeah. Okay, so here, you basically, for extended system, you can ask how does perturbation grow in time and also spread in space. And so typically you have this light cone, and then the slope of this light cone is the butterfly velocity, and we have expressions for renormalized butterfly velocity. So yeah, I'm done. Okay. So we have these expressions. So let me show you a diagram. So the left plot is when there is no resetting. This is this coupled map lattice. You take this logistic map and you sort of generalize it. You have this nice light cone. This is the slope of the cone, and the slope starts becoming more and more as you increase the resetting rate. And at some critical resetting, you completely arrest the system. So you stop the spread of information. And these are the agreement between theory and analytics for various quantities. So let me just conclude by saying that stochastic resetting is sort of a powerful mechanism, especially in terms of analytics for mitigating spatial temporal chaos. It can induce a dynamical phase transition where spreading of information can be brought to a complete halt. These results can be easily generalizable to continuous time dynamics, although I've spoken about discrete maps. And we are working on using these kind of techniques for studying other interacting classical many-body systems. And quantum resetting is sort of a very fast-growing field now. And we can ask the same question for quantum systems. What happens if I reset a quantum system to some initial state and study quantum chaos? Thank you.
Some quick question?
Yeah, so when lambda becomes, when this resetting rate becomes RC, it essentially, Lyapunov just vanishes. So we get chaotic and non-chaotic transition for certain, yeah.
At that time, Laplace exponent should be negative for fixed point.
No, so the point is, it goes back to, what we see is that both numerically and analytically, the Lyapunov exponent becomes 0, but it really doesn't go negative. So this is what we see. So if I take a completely say damned harmonic oscillator or something like that, I would get negative Lyapunov. But here the formation is such that I get 0 Lyapunov exponent. So yeah, this is something we still not quite, but really we were also a bit puzzled by this. But let me just show you this. Yeah, so you see that we went all the way, and this is numerics and analytics. So maybe there's more to it after R critical, which may not be fully clear. But yeah, we see this. Yeah.
Okay, I didn't quite understand. So when you do a resetting, does the return map, does it still remain a unimodal curve or no?
Sorry?
You plot xn plus 1 versus xn, does it still remain a unimodal curve or no?
No. So you keep on updating it, and then at some random time you make xn plus 1 to be x naught, and then again repeat it.
Okay.
Yeah.
Okay, so let's thanks our speaker.